In this video, we are going to discuss about Coulomb's law, the relative permittivity, Coulomb's law in vector form, and the force between two charges in terms of their position vectors. Let's get started. So, first is Coulomb's law in electrostatics. In 1785, Coulomb measured the force of attraction or repulsion between two electric charges. His observations are known as Coulomb's law in electrostatics. And the Coulomb's law states that the 2-point charges attract or repel each other with a force which is directly proportional to the product of the magnitude of the charges and inversely proportional to the square of the distance between them. So let's take 2-point charges Q1 and Q2, and the distance between these two charges is equal to R. Then the force between these two charges F is directly proportional to the product of the magnitude of these two charges, means multiplied by Q1 multiplied by Q2, and this force is inversely proportional to the square of the distance between these two charges. So this implies the force is directly proportional to Q1 Q2 divided by R square. Now we remove this proportionality sign with equality. So we'll write this force F is equal to K Q1 Q2 divided by R square. This is the formula. But always remember this K, the proportionality constant, always depend on the nature of the medium used. The medium can be air, water or anything else, and also it depends on type of system of unit we are using, whether it is CGS system or SI system. So here in case of the SI system, this K is equal to 1 upon 4 pi epsilon naught, and this here the medium is vacuum or air, and this epsilon naught is known as absolute permittivity of the space, and its value is equal to 8.85 over into 10 raised to power minus 12 Coulomb square Newton inverse 1 and meter inverse 2. And the value of this 1 upon 4 pi epsilon naught is equal to 9 into 10 raised to power 9 Newton meter square Coulomb inverse square. So here we can write this force in vacuum as equal to 9 into 10 raised to power 9 multiplied by Q1 Q2 R square, and the unit of this force is equal to Newton. Now let's discuss relative permittivity dielectric constant. Suppose we placed our charges Q1 and Q2 in a medium. This medium can be a water and anything else. Then this epsilon naught will change to epsilon. Suppose we have placed our charges Q1 and Q2 in a medium. This medium is water, and the distance between these two charges is equal to R. Then the force between these two charges is equal to, we write here medium, 1 upon 4 pi epsilon Q1 Q2 R square. So we know the vacuum, this force is equal to 1 upon 4 pi epsilon naught Q1 Q2 R square. Here R square will come. So if we divide these F vacuum and F in medium, then we'll get this 1 upon 4 pi epsilon naught Q1 Q2 divided by R square and divided by this vacuum, force in vacuum, which is equal to 1 upon 4 pi epsilon naught Q1 Q2 R square. Then we'll get this F vacuum divided by F in medium is equal to epsilon divided by epsilon naught. This ratio, the epsilon and epsilon naught ratio, is known as the relative permeability. So this we represent with epsilon R. So this implies this epsilon R is equal to F vacuum divided by force in medium. So this is the formula for the relative permittivity. So means we are comparing the permittivity of the medium with vacuum. Now let's discuss the Coulomb's law in vector form. We know the force is a vector quantity, so it means we can write the force between two charges in vector form. Let's see how we can write this. So here we have taken a system of two like charges Q1 and Q2. So here Q1 and Q2 are like charges and the distance between these two charges is equal to R. These are like charges, so they will repel each other. So it means this charge Q2 will apply a force on charge Q1. So as they are like charges, they will repel each other. So it means this force will be toward left hand side and this force will be represented by F12. Similarly, the charge Q1 will apply a force on charge Q2 and that force will be toward the right hand side as they will repel each other. So this force is equal to F21 vector. So we can also write the unit vector related to this Q1 charge as 1R12 unit vector, and the unit vector related to the charge Q2 we can write it as unit vector Q1. So in the vector form we can write F12, the force applied by charge Q2 on Q1 is equal to, as we are taking the medium vacuum here, so this is equal to 1 divided by 4 pi epsilon naught Q1 Q2 divided by the distance between two charges, which is equal to R square, and R21 unit vector, as this unit vector and this force has the same direction. So this is the vector form of the Coulomb's law. Similarly, we can write this F21 vector is equal to 1 upon 4 pi epsilon naught Q1 Q2 R square, the distance between two charges, and here the unit vector will be R12 unit vector. This is our force, and we know this R21 unit vector is equal to negative R12 unit vector. So if we put this, so we'll get here F12 is equal to negative F21 vector. So from here we can say that these two forces F21 and F12 are equal and opposite. The last topic for this video is the force between the two charges in terms of their position vectors. Now we are placing these two charges in a coordinated frame. So now we have placed our two charges, like charges Q1 and Q2, in a coordinate frame OXYZ. Let me take this as point A. At A we have placed charge Q1 and at point B we have placed charge Q2, and the position vector of this is equal to R1 vector and this is equal to R2 vector. So OA vector is equal to R1 vector and OB vector we have taken as the R2 vector, and the distance between these two charges similarly we have taken as R. So AB is equal to R vector. So as these charges are equal, similarly will force on charge Q1 due to Q2 will be toward that side, and this force will be represented by F12 vector, and the force on charge Q2 due to Q1 is equal to F21, and this will be toward this side as they are equal charges and they will repel each other, correct? So we can write, and the unit vector R12 will be toward that side and unit vector R21 will be toward this side. We can write F12 is equal to 1 upon 4 pi epsilon naught Q1 Q2 divided by R square R21 unit vector. Now we can write this as 1 upon 4 pi epsilon naught Q1 Q2 R cube into R R21 unit vector. So here I have multiplied and divide this whole thing with R. So this is my F12. correct. Now we'll apply this triangle law of addition to this triangle OAB. So we'll see here that OB vector plus BA vector is equal to OA vector. From here we'll get BA vector, which is equal to OA vector minus OB vector. So this is OA is equal to R1 vector and OB is equal to R2 vector. So this implies this BA is equal to, which is R vector, R1 minus R2 vector. You know that we can write this unit vector R21 unit vector as R vector divided by R vector magnitude, which is equal to R. So we can write this BA in this form also. So this R, multiply this R21 vector is equal to R vector, which is equal to BA. So we can put this value here. So this implies this is equal to R21 unit vector is equal to R1 vector minus R2 vector. And this is R vector is equal to R1 vector minus R2 vector. So this R vector magnitude is equal to R vector minus R2 vector magnitude. So we'll put this and this here. So we'll get this F12 vector is equal to 1 upon 4 pi epsilon naught Q1 Q2 divided by R cubed, which is equal to R1 vector minus R2 vector modulus multiplied with is equal to R vector, and which is equal to R1 vector minus R2 vector. Here the Q will come. So this is the force on two charges in term of their position vector. Similarly, we can write F21 is equal to 1 upon 4 pi epsilon Q1 Q2 divided by R2 minus R1 vectors modulus 3 R2 vector minus R1